Okay, so the question asks, well, what input must D and E be for the output to be 0? So we're interested in the Q output. And then this one is always opposite Q prime, as you see, as we trace through the circuit. So let's do like a standard truth table for D and E. 0, 0, 0, 1, 1, 0, and 1, 1. And then on the other side, we have our output Q. So if we put D as 0 and E as 0, we would see that this is NOT gate, so we'll make this 1. E is still 0 here, so the result of the AND is a 0. E is 0 already, so it doesn't really matter what the other value is. For AND gate, both has to be 1s for it to be 1. And we come to these NOR gates, but you're saying, well, it depends on the output for the input. So what is the output? Well, let's make assumptions for now. Let's assume Q is 0. So that means 0 comes here, and 0 nor 0 is a 1. So this makes sense. And 1 comes back, that's a 0, right? Okay, so what if we have a different value? What if we have 1 instead? We should actually use a different color. Then 1 will propagate here, nor will become a 0, and then 0, 0 will become a 1. So as we can see that the 1 actually stays, and if you have a 0, the 0 stays as well. So if both are 0, then Q would actually be Q would be whatever Q was before. And then we can go to the case with 0 and 1. This time we'll use a different color. Okay, so D0 is 1. When D0 NOT gate, this is still 1. E is 1. This becomes 1. So this AND gate outputs 1, but this one is 0 and 1. So this one is 0. So 1 comes here, and we have to assume the outputs again. So assume Q starts at 0. Then this one is 0. This one is 1. 1 propagates here. When you have two 1s, your output 0. Okay, that makes sense. What if we have different values? What if this one was a 1? Then 1 propagates here. 0 and 1 becomes 0. This becomes 0. And 1, 0 becomes 0 again. And you're saying, wait, this is a problem. They can't both be 0. Well, 0 propagates back down, and this becomes a 1. So this will eventually stabilize, because if 1 comes here, then it's going to output 0, and then 0 comes here, it's always going to output 1. So as we can see, we set 0, 1 to 0 all the time. Let's do one more case. Let's do a 1 and 0. Wrong color. Okay, let's say D is 1 and E is 0. Then 1 comes here, 0 comes here. Oh, this is actually 0, my bad, through the NOT gate. And then this will be 1 and 0 here. So both of these are 0. And let's assume outputs again. Let's assume Q 0. 0 comes here, this becomes a 1. 1 comes here, this is still a 0. Okay. Erase. Let's assume Q is a 1, then 1 comes here, 0 and 1 is a 0. I wrote it already. And then 0 comes back here, and 0 is a 1. So as we can see in this case, 1, 0 is still going to come out to be Q. We won't do the last case because it will make the video too long. But 1 and 1 is going to come out to be 1 because you'll overwrite this. So go back to the question. In this case, for Q value to be 0 independent of Q, D will need to be 0, and E will have to be, which is usually known as an enable bit, is going to be B. And through our diagram, we can see these two are Q, and what value of E will keep the same? Well, when you have an enable bit of 0, they will be the same. So we might as well cover what kind of logic circuit is. So as we can see, this is a sequential circuit because the input, your output is dependent on your previous output. So right here, your output loops back, and then your output loops back right here. So this would be one of the sequential logic circuits. And which one would it be? So it's actually going to be asynchronous sequential logic circuit because it's not dependent on clock. As we see, there's no any pulse or clock here. There's just 2 bits that we're inputting. So that's why it's going to be F.